Good afternoon, distinguished guests, colleagues, and students. On behalf of the Faculty of Engineering at the University of Hong Kong, it's my great pleasure to extend a warm welcome to you all for this William Mong Distinguished Lecture and the workshop. Hong Kong Engineering is deeply committed to fostering knowledge sharing and inspiring the next generation innovation through engaging academic seminars and workshops with industry leaders. Today's gathering is a shining example of this commitment. This distinguished lecture, as you heard from Professor Liu, is made possible through the strong support of Dr. William Mong. Today, we also start a workshop together with the Keynote section, bringing together famous researchers to strengthen Hong Kong U and the Global Innovation Hub. We are privileged to invite Professor Robert Heath, a top scholar in the field of wireless communications, to give a lecture on the evolution of MIMO in cellular system. And following this keynote, we'll have a panel workshop moderated by Professor Huang. This is a unique opportunity for us to deep discuss how to shape the future of the wireless technology. I would like to thank everyone here, our speakers, our panelists, and also our audience. Your presence makes this exchange of ideas possible. Thank you. And before we start the lecture, it is my great honor to present a gift of our Faculty of Engineering to Professor Heath. Please, Professor Heath. Yeah. Hi, Professor. It's a gift from our faculty. We have photographer to take photo of us.
Okay. Excellent.
Okay, yeah. They have highlight this.
I see.
Yeah.
Okay, ready? Okay,
Yeah,
ready.
ready.
One more. Okay. Thank you.
Okay. Yeah. Maybe also Professor want to say that. Yeah, you put this. I think on this side. Yeah.
Okay. Okay, ready? 3, 2, 1. One more. Okay. Thank you.
Thank you. Thank you. Thank you. Okay.
Yeah.
Okay, thank you. So now let's pass the stage to Professor Robert Heath's lecture on unlocking MIMO in 6G, the evolution of the MIMO in the cellular system. Now it's your time, Robert.
Okay. Okay, excellent. Well, I'm pleased to be here and to give this distinguished lecture and keynote and to talk a bit about the history of MIMO communication, an area that I've been exploring since my PhD, and tell you a little bit about some of the background and talk about where I see MIMO headed in the future of 6G. I appreciate the contributions of my colleague and fellow panelist, Professor Gonzalez-Prelchich, who's allowed me to use some of her amazing slides. The slides that aren't very good, those are the ones I made. So I'd like to kick it off here just with a little bit of background about San Diego. As you know, we're in California and USA. California is almost a separate country at this point in terms of the way it thinks and for other reasons. Our campus, this is our Jacobs Hall, which is the main headquarters of the electrical engineering, the Department of Electrical and Computer Engineering and the Jacobs School of Engineering. And indeed, it does have this very odd house that is at a weird angle on the top. It's pretty cool. I actually have yet to be in it, but I'm told it's amazing. We have a lot of nice sculpture, some amazing laboratory facilities, and of course, the beach and the sunsets there. So I wanted to kick off this lecture here, before I get into the details of MIMO communication, I wanted to spend some time just talking about wireless fundamentals and, what is wireless communication, what are some of the key terms, and then we'll get into the main topic of today, which is multiple antennas. Let's start off here with just a little bit about, what is wireless communication? I mean, the obvious thing is it's communicating without wires. We typically have a transmitter and a receiver, and we use these little triangles on the sticks there to denote the antennas that are used for transmission and reception. And this is using radio frequency signals, launching this radiation into the propagation environment. It bounces off various objects in the environment and lands at the received signal through the propagation channel. So some of the concepts that are really important in wireless, I wanted to draw your attention to two here, which is frequency and wavelength. So you might remember from, I assume most of the audience here is in electrical and computer engineering and has probably taken or will take shortly a class on signals and systems. And you learn all about the Fourier transform and the importance of sinusoids in electrical engineering and engineering more broadly. It's a little bit of background about sinusoids. Sinusoids are shown up here. There's different oscillations, and they're associated with a frequency. And the higher the frequency of the sinusoid, the faster it oscillates. Frequency and wavelength are inversely related. So the higher the frequency, the smaller the wavelength. The wavelength is the difference between those two tips there. In wireless communications, we use signals at different frequencies to send information. And some of those wavelengths can be as big as hundreds of meters in the high frequency bands that are used for amateur radio, to tens of centimeters for cellular communication signals, and even up to millimeters is used in millimeter wave 5G cellular communication and Wi-Fi. And so there's a whole lot of different communication frequencies that are being exploited in wireless systems. So after this little introduction of frequency, there's a couple more concepts that are really important. So we send information in wireless systems by modulating one of those frequencies. So in a sense, we take that sinusoid and we multiply it by another signal, and that other signal encodes information. And the more, the higher the frequency of the sinusoid, or the more fluctuations of the signal, it consumes what we call higher bandwidth. So the bandwidth is the measure of around the carrier frequency of all of the sinusoids that are building up that signal there. And so if you have a sinusoid with a lot of fluctuations, it will consume more bandwidth than a sinusoid with fewer fluctuations. And in wireless systems, your bandwidth is your real estate. So bandwidth is something that is normally heavily regulated by every government. And not only is it regulated, it's often licensed and auctioned and sold. It's used to generate money and revenue for the government, just like a piece of property. And so generally speaking, having more bandwidth is something that is very good for the wireless applications, and it also leads to higher costs, and it's consuming a bigger piece of real estate. So now let's get into some of the more details about wireless communication systems here. And this slide, honestly, was more applicable when I was in Austin, and there were a lot of pickup trucks around. In San Diego, it's more like Teslas. But anyways, we didn't have time to change these up here. So there's two important concepts in wireless. One of them is spectral efficiency. So the ability of sending information on one of those sinusoids is determined by how good the propagation environment is and how much noise there is at the receiver. And so we can think about this in terms of pickup trucks carrying bits. If you have a truck that's going on a gravel road, not paved road, is really bumpy, you can't take too many bits because a big truck won't fit. But if the road is smooth, and you can use a bigger truck and you can carry more bits. So the spectral efficiency is somehow a function of the propagation environment and the parameters of the receiver there. And it's a measure that's bits per second per hertz. So it's really how efficiently it's possible to use the real estate, the road in this case. Now the second situation there, I'm sorry, some of my colors don't show up on the screen. It's kind of weird. They're supposed to be like roadways with lines there. I see it on my screen, but I don't see it up there. So you can see it there. Okay, interesting. Well, I don't know. You can see, okay. Anyway, I won't speculate on what's happening here. So what you can see over there is that we have a highway that's got 3 lanes. So we can have 3 trucks carrying the bits cruising around at the same time. So in this case here, I'm using as bandwidth the number of lanes. So on the right side, we have a larger bandwidth than on the left side. And over here, we have a low spectral efficiency, so small truck, few bits, high spectral efficiency, big truck, many bits. And the data rate that's achieved in a wireless communication link is the product of these two. It's the spectral efficiency times the bandwidth, right? So of course, if we had 10-lane road, we could have 10 trucks going at the same time. So now let's get into a little bit of the meat of the discussion here in this lecture, which is about cellular communication systems. So cellular systems, we're all widely used, use a network of base stations. These are the base stations here. They're networked together by wires that you can't see. And they're networked together and they're providing wireless communication services to many different devices. I mean, people, smartphones, vehicles, robots, any number of things in the environment there. And these cellular systems are, becoming smarter and supporting even AI and ML type applications. Now, the cellular concept is related to the data rate in the following way. So imagine like in the city of Hong Kong, we put 1 base station here. And you're going to cover the entire city with 1 base station, right? There's, I don't know how many million people are in Hong Kong. You would barely be able to make a connection. You wouldn't be able to send too many bits because everybody is fighting to access that 1 base station and share all of those resources. So the miracle of the cellular concept is that instead of having just 1 tower and 1 set of bandwidth, what we're going to do is we're going to split up the area geographically. We're going to put a base station on top of every building, maybe inside every building, on every floor, and every room at the extent. And what happens is we're going to reuse the same frequency, the same bandwidth, and have more base stations. And when you do that, even though there's interference between the base stations, it becomes possible to reduce the number of users that are accessing each base station. And that fewer users per cell actually trumps the effects of a little bit of interference between the cells. And so what you get in a cellular system, which is interesting, is that now the rate per user is the product of spectral efficiency and bandwidth divided by the number of users per cell. And the more cells that you have, the fewer users per cell. I mean, the ideal situation would be in this room, we'd have like 10,000 cells, and everyone would be like in their own cell, and we'd get all the bandwidth for our cells. That's the cellular concept. Now, by the way, there's natural issues associated with densifying cellular systems, like it's expensive. You got to get leases to put your towers on the buildings, and you have to pay money per month to the building owner and to pay for the power and so on. So it's not a free lunch, and you can densify, to some extent, but as far as like putting 1,000 base stations in this room is not really feasible here. So spectral efficiency and bandwidth in cellular systems have been growing. So this is a slide that we put together based on the different capabilities of 2nd generation cellular systems, 3rd generation, 4th generation, and 5th generation. 5th generation is what you all are probably using. When I started my career as a PhD student, that was when 2G was widely deployed. And there were these great debates about what 3G should look like. And there was this TDMA, CDMA war, and CDMA ended up winning here. There's a lot of nuances associated with the numbers here, but the net of it is that bandwidths have been increasing over time because these releases that I'm showing here, 2G happened 10 years before 3G, which happened 10 years before 4G, and so on. And then the spectral efficiencies have also been getting better. And by the way, this doesn't mean that you're necessarily getting the high spectral efficiency. It just means that the system supports the high spectral efficiency. So these are like ideal numbers here. And the bandwidth per carrier, that's a pretty big number. This is kind of like if you were able to aggregate all the bandwidth available to cellular, it would be like down there. But the net of it is spectral efficiency and bandwidth have been, increasing. So now let's get to the matter at hand of the talk here, which is MIMO communication, multiple input, multiple output communication systems. And I'm going to explain this block diagram more, but the net of it is I'm going to talk about wireless systems with multiple transmit antennas and multiple receive antennas. So here's a system with multiple transmit and multiple receive antennas, but this is like the one I showed you before. There's a transmitter and a receiver, and I put in another transmitter and another receiver. And they're using the same frequencies. And they're each transmitting, trying to communicate with their respective receiver, and they're interfering with each other. And if these users are far apart, like in a cellular context, maybe the communication can happen, but if the antennas of the users are close together, there's a lot of interference, and it's really hard to get a high spectral efficiency. It's kind of like two cars, tailgating each other on the highway. I mean, they end up going slower because you can't go as fast, super close together. So now, what if, instead of having two separate users, what if both of those antennas were connected together in a joint receiver? So we have what's called an antenna array, several antennas put together. And so those several antennas put together listen to the transmissions from transmitter 1 and transmitter 2. Now, if we intelligently combine those signals from the antennas together, it becomes possible to do something called beamforming. And in PowerPoint, this little oval collection is a beam. It's a little more complicated than that in real electromagnetics, but that's what it looks like in PowerPoint here. And what this antenna array is doing is it's focusing its sensitivity on the signal from the first user. Now, it turns out that it's also possible to take that received signal and pass it through another spatial filter, which is a beamformer, and focus on the second signal. So if you have two antennas, you can form a beam such that it's possible to filter out one transmission from another and decode the signals from both of those different transmitters at the same time. This is called spatial division multiple access or multi-user MIMO. I'll talk a little bit more about this here. So by aggregating all the antennas together, you can actually support multiple transmissions, whereas this wasn't really possible before when the receive antennas were separated here. And so this beamforming is possible because of that coordination there. So now we get to a thought experiment. And this is something that I got familiar with as a PhD student. My advisor, Professor Paul Raj at Stanford, he was a very good theoretician, but he had a lot of practical experience. And so he was able to come up with what he called thought experiments. They were basically very simple questions that didn't have any obvious answer and often would lead to your dissertation. And so that was like what he would do here. He would bring us into the office and be like, okay, so what do you think about this? And draw something simple on the board, and then we would go back and think about it for 6 months. That was kind of my PhD experience. So a thought experiment here. Okay, so if my joint receiver can decode the signals from both of those two transmissions, what if both of those two transmissions were also an antenna array on one device? Would this still work? And it turns out the answer is yes. And this leads to the concept of spatial multiplexing. So what spatial multiplexing does is we take data. In this case, I'm showing the data as a sequence of letters, A through F. And I'm alternately sending A on one antenna, B on another antenna, C, D, E, and F. And I'm sending over here these 6 letters. I'm sending them in only 3 time periods here. So by multiplexing the signal, really demultiplexing in space, I'm able to send twice the amount of data in the same amount of time as otherwise I would have sent one symbol. And this data is, it's not the data for 2 different users, it's the data from one user being split across the antennas. And this is the MIMO spatial multiplexing concept, and this is why MIMO communication. When people talk about MIMO, they're really talking about a wireless communication system that supports spatial multiplexing. So let's get back to the pickup trucks here. So a MIMO communication system. Well, those multiple antennas, they transmit signals that go into the propagation channel. Those are called inputs. And the signals from that propagation channel are received by multiple antennas. Those are at the outputs here. So a MIMO communication system uses a MIMO channel with multiple inputs coming from the multiple transmit antennas and multiple outputs coming from the multiple receive antennas. And coming back to the, what happened here? Coming back to the highway setting here, MIMO is like building your roads in the vertical dimension. And in Austin, they actually had this happen. The interstate double stacked through downtown Austin here. So where I had 3 lanes before, now I've got 6 lanes. So I've got 6 pickup trucks carrying the bits at the same time. And you could keep building up and up, right? Now, of course, just like in reality, if we were to try to build a highway that was stacked 10 on top of one another, there's all kinds of practical engineering details that would make that challenging. And that's the case in wireless too. So, generally speaking, one might be able to get a few highways stacked on top, and it's harder and harder to get more and more highways here. So the benefits of MIMO can be plugged into our rate per user equation as a multiplier on top of the spectral efficiency to bandwidth and the users per cell. So what you can see is that if you don't have a lot of bandwidth in a wireless system, you could use a lot of antennas at the transmitter and receiver and overcome that lack of bandwidth. Or if you have a good amount of bandwidth, you can use the MIMO capability to get even more data than you could have gotten before. This scaling factor here is generally the minimum of the number of transmit and receive antennas, and could be 2, 4, 8, something on that order there. So this is MIMO communication, spatial multiplexing, and if you fall asleep in the rest of the talk, at least remember this one here. So I was asked to talk a little bit about the origins of MIMO communication, and I think this is one that I started looking into this, and I went down a rabbit hole of trying to figure out where did MIMO actually get created, and I gave up. It was hard. So I wanted to give you just, from my perspective, when I teach a course on MIMO communication, I teach a course on information theory for MIMO systems based on my textbook that has sold so much. I bought 1 cup of coffee last year, and I might be able to buy one next year too, if you all use it in your course. It's not a lot. Nobody writes a book in academia to make money, it turns out. But they don't tell you that when you sign the contract. You think, oh, I'm going to be rich, I'm going to retire early, and then you realize that nobody wants to buy a book on MIMO information theory. Who knew? Who would have guessed? So multiple antennas actually show up in almost the earliest experiments in wireless communication. Some of the early work, you can't see this, it's a copy from a paper that has a copy of a photo of this early experiments of Marconi. But the net of it is that multiple antenna elements have been around almost as long as wireless communication itself. The concept of MIMO in the sense of spatial multiplexing, there's some work in the 80s that foreshadowed the development of MIMO at Bell Labs, some interesting work in polarization that I was trying to dig up, but I didn't get good references to show you here. The one I'm most familiar with is the development by my advisor at Stanford. It's a patent by Paul Raj and his mentor, Tom Kailath. And they developed, this was back in the days of discussion about digital TV. And the idea was like, okay, how can I get digital TV to work in a 6 megahertz TV band when I need 18 megahertz of spectrum to convey that digital signal? And his idea was, well, we're going to take that signal, divide it up into 3 6 megahertz pieces, transmit each from a different antenna, and put them all together with an antenna array. Exactly the spatial multiplexing idea. And it's actually explained beautifully in the patent, one of the best written patents. I think Paul has told me he actually wrote the patent himself. Most patents are written by attorneys who deliberately try to confuse the situation in the patent to make it valuable later because none of the terms mean anything. But I digress there. And then in parallel here, this happened at Stanford in the early 90s. But most people know of the work from Bell Labs, the vertical Bell Labs layer space-time architecture. Started developing in 94, 95, 96. They built a prototype. Foschini wrote a really nice paper on the data rate capabilities of MIMO. So that got a lot of attention. And then I was involved in a startup with Paul Raj that was leveraging his patent to try to commercialize MIMO technology. That company was a complete, well, I wouldn't say complete failure, but it didn't make any money for me. And then he basically started the company again, and then that one got a lot of money. But I was a professor at that point, so I didn't get anything. So the origins of MIMO, really, I would say, MIMO as we know it in cellular is in the mid to late 1990s. And let me give you a little snapshot of how MIMO has been evolving in cellular systems over the years. And also I'm putting in wireless local area networks as well. So MIMO didn't end up in any commercial standard until about 2004, and that first one was the wireless local area networking standard, 802.11n, and it supported 2 transmit and 2 receive antennas. The scale should be down a little bit here. And then later on, 4G also supported 2 transmit antennas, and then the support for MIMO has continued to increase up to 128 antennas at the transmitter and 8 antennas at the receiver. This is single user mode. And this doesn't mean that all of our devices have 8 antennas or 128 antennas. It just means that this is supported in the standard. And there's discussion in release 19 and beyond about increasing the number of antennas at the base station even further. And you know, looking at this picture here, we don't need a neural network to gather that. It's probably going to keep going up, you know. So MIMO is going to continue to increase and continue to be supported in a bigger extent in cellular systems. So MIMO nowadays has blown up, and MIMO can mean many different things. There's multi-user and massive MIMO, where there's a lot of antennas on one side, like the base station supporting many users, possibly with multiple antennas. There's MIMO with relays or reflective surfaces, where there's some intelligent control of the propagation environment. There's MIMO where the base stations are all coordinated together and data is distributed across all of those antennas. And those antennas are like distributed geographically, but it's like one big MIMO network. Cloud RAN, distributed X antenna systems. And then there's even work outside of cellular and MIMO for ad hoc networks, for military radios. So MIMO has, in the last 20 years, has just been a technology that's been widely deployed and adopted in many different places. So I want to move on now and talk about some of the more recent developments in MIMO, starting with millimeter wave and hybrid MIMO processing here. And what's going to happen is I'm going to explain to you why this MIMO block diagram has expanded in complexity and why that happened here. So back in the early to say 2010s or so, there was some initial work that was done to show that millimeter wave spectrum could potentially be used as cellular. So cellular systems at the time, the frequencies that were being used were primarily below 3 gigahertz. So there was some spectrum around 800 megahertz and spectrum around 1900 megahertz and 2100 megahertz. And that was primarily what was used for 4G. A little bit of spectrum above 3 gigahertz there. And the problem is that spectrum, this is an FCC spectrum chart, and these, you can't see the numbers here, but these are little slots of bandwidth. And these slots each have a bunch of different people that are sharing that spectrum. There might be satellites and radars and sensing, and the channels are small. There's not a lot of bandwidth to be had. There's maybe 5, 10, 20 megahertz in these channels. But if you go up to millimeter wave, you can get channels that are hundreds of megahertz or even a gigahertz wide. And so what was recognized here was that it might be possible to increase that bandwidth multiplier by like a factor of 10 by going to millimeter wave. So this was a way to go from 2 lanes to 20 lanes all at once, going to millimeter wave. And so that was started to be looked at in around 2010, and it was became a big part of 5G. One of the defining features of 5G and one of the most cited failures of 5G as well. Millimeter wave, people were under the impression it was a new technology, but actually it wasn't really new technology. Some of the earliest wireless experiments done by Bose in India actually were at millimeter wave in the 60 gigahertz band. So millimeter wave is also very old, though admittedly it wasn't as widely used as the lower frequencies, in part because millimeter wave didn't propagate as far. So like the early experiments of Marconi were sending signals across the Atlantic, and that's hard to do at millimeter wave. So it wasn't as popular of a practical technology for many, many more years. But millimeter wave was used for different applications. One of the earliest ones was in World War II for fire control radar. This was a radar that helped to direct bullets that were being shot at an airplane, kind of a depressing thought. But that was one of the first applications of millimeter wave, been used in radio astronomy, automotive radar, satellite-based remote sensing, security screening. When you go through that naked body scanner in the airport, that's millimeter wave. And then started to appear in some commercial applications, including 5G. And I mentioned here, in most parts of the world, millimeter wave hasn't been a huge success, not because the technology doesn't work, but really because it wasn't deployed in a way to make it work well, at least in the US and other places. And I can talk more about that later here. So let me explain what is the connection between millimeter wave and MIMO communication. Because millimeter wave is about bandwidth, right? And MIMO is about antennas and spatial multiplexing. So what's the connection? Well, the connection is as follows here. When you go to a higher carrier frequency, the wavelength shrinks. Remember, I showed you that picture earlier. And the smaller antenna, it doesn't capture as much of the energy that impinges on it here. So when you go from like a green, a lower frequency, to an orange, higher frequency, you get less of the energy at the receiver here. So there's what people call a path loss. It's not really a loss, it's just that you're not getting as much of the energy there. So the antennas get smaller, and that's a problem. So what can happen here? Well, you're probably already guessing that what you could do is you could have a bunch of those small antennas networked together in an antenna array. And by doing that, then you can use beamforming, and you can overcome that loss due to shrinking antenna sizes here. And you can actually capture the same amount of energies at a lower frequency signal here. So this smaller antenna array fixes that shrinkage problem. Now, where does MIMO come in? Well, when you go to higher bandwidths, the noise power is also higher, and the transmit power is the same. So the SNR is worse. So it turns out that you can also put the antenna array at the transmitter and focus the energy towards the receiver and get a gain from the transmit focusing, a gain from the receive focusing. And this overcomes the small antennas and the small bandwidth. And sorry, the bandwidth increase here. So multiple antennas became something that's really necessary to make millimeter wave technology work. So let me explain a little bit about what were some of the issues with millimeter wave. Well, one of the challenges is that if you looked at the way that we were thinking about MIMO in the 2010s, all of the MIMO processing, all that beamforming was being done in a digital signal processing, ASIC and FPGA. And there was that signal was converted to analog with a DAC, there was an RF chain, a power amplifier, multiple antennas. And what happened is that the power consumption, so if you wanted to go from 3 gigahertz to 30 gigahertz, you needed 10 times the number of antennas to take up that same space maybe. And then you want to go from more antennas also to more bandwidth. And so the DAC, the bandwidth, the power consumption increases with bandwidth. So having larger arrays and higher bandwidth made this original fully digital MIMO architecture consume too much power and made it not very practical to have hundreds of antennas with 500 megahertz or 1,000 megahertz of bandwidth. So this led to the development of what's now called the hybrid architecture. It's a hybrid between analog and digital beamforming. There's some digital signal processing and some analog signal processing, some co-phasing, some combining, some attenuating that happens together. And maybe you have 10 outputs from the digital and 100 outputs in the analog. And there's this analog filtering that's happening here that takes you from 10 to 100. So it becomes a way to push off some of the high power consuming components to have fewer of them and reduce the overall power consumption so that you can grow the size of the antenna array without growing the power as much. And this hybrid architecture became the way that we started thinking about MIMO in millimeter wave communication systems, and it changed how MIMO looked. And this is what the hybrid MIMO architecture might be in a fully MIMO system with multiple transmit, multiple receive antennas. There's a digital analog potentially on each side. And there's a lot of challenges that are associated with going to a hybrid architecture because one of them is like the way that the communication signal is perceived. It gets filtered by these large arrays. And so it becomes much more complicated to design the algorithms, to configure the MIMO communication link, to estimate it, to feed it back. So all of the main features, the ways that MIMO were used in 4G needed to be changed. And they were changed, and 5G adopted something called beam management, in part because of the hybrid architecture, to support configuring the analog by trying a few different beams, and then configuring the digital by refining those beams and feeding back. And I'm simplifying many things here a bit, but the way that MIMO evolved in 5G was really to support the hybrid architecture that was proposed for millimeter wave. And this beam-based hybrid architecture became a key feature of 5G at both the lower frequencies and the higher frequencies. And so MIMO became an important part of millimeter wave and 5G. So now the last few minutes, I was already given the note that I'm running out of time. I didn't have enough coffee today, unfortunately. It's only like 6 cups. I need to get to at least 8 to go fast enough. I'm going to talk about the tri-hybrid MIMO architecture. What is the tri-hybrid doing? The tri-hybrid is introducing, so here we have a pair of digital signal processors, a pair of analog signal processors. Now we've replaced our antennas with another box. Let's see what that's all about. So the motivation for me for the tri-hybrid, in part, is this forgotten spectrum. So before I was telling you that, well, cellular is using like 6 gigahertz, and they want it to go to millimeter wave above 30 gigahertz. But what about in between, like 3 to 30? Why not go there? That spectrum is pretty crowded, but now there's interest in using that spectrum. That spectrum, it penetrates buildings better. There's a lot of reasons that that spectrum might actually be more interesting than millimeter wave. You can get higher bandwidths there. It's just very congested with lots of incumbents. That spectrum is called the upper mid-band and has now been targeted for use in 6G, the World Radio Research. I forget actually what WRC is, but essentially some of those bands, 7 gigahertz and 15, have been targeted for early use by cellular and will be part of either 5G advanced or 6G here. And so what's interesting is, so 6G may start targeting this new spectrum that was between the old spectrum and the millimeter wave, centimeter wave spectrum. And what the challenge is, when you go from, say, 3 to 15 gigahertz, the aperture, it's the same story I showed you before. So the antennas get smaller. So we need more antennas, fine. But one of the things that people want to do is they want to deploy those antennas in the same spacing as the lower frequencies. So you actually need more array gain to not only overcome the bandwidth that's bigger, but also the larger loss from the bigger spacings of the antennas here. So you need even bigger arrays. And white papers by Qualcomm and Nokia are suspecting that the array sizes could grow from what was supported in 5G of maybe 256 up to 4,000 elements or more. And if you take that hybrid architecture and you try to extend it to 4,000 elements, so we have 400 digital outputs and then going to 4,000 antennas, the power consumption is too high. It seems like it's not going to work. So the idea that we've been pursuing, and this is an area now that many folks in the community are looking at, is to exploit reconfigurable antennas. So these are antennas where they can be, the pattern itself can be changed by changing properties of the antenna. And this could be done in an electrical way by changing a resonance. It could be done in a mechanical way by shifting something. It could be done in a material way by changing the properties of some metamaterial. And electrical reconfigurability is good and wireless is fast, but there's many ways of doing the reconfiguration. And the reason that we find this interesting is that a reconfigurable antenna, you can also do some beamforming. So you can create directive patterns, but the directive patterns can be created with much lower power because changing the bias voltage of a varactor diode doesn't consume nearly as much power as this big complicated network that's used for hybrid precoding in the analog. And so this brings us to the tri-hybrid precoding architecture that I hinted at before. The tri comes from now there's 3 layers here. There's a digital signal processing layer, an analog signal processing layer, and an EMAG signal processing layer. So effectively, you can imagine that we have a reconfigurable antenna that replaces what would have been 10 antennas before. And we attach that to a hybrid architecture. So we've got like 10 digital going to 100 analog dimensions, going to 1,000 reconfigured antenna elements there. And this layer of reconfigurability is typically very low power. So when we combine it with a hybrid architecture, we can bring the power down and maybe make large arrays feasible for high bandwidth in the upper mid band. And I think it's a very interesting area to investigate, and this is, for me, the most exciting part of MIMO that's being looked at in my group. So I try to wrap up now. So in terms of new research challenges, when we incorporate smarter antennas into a MIMO communication system, everything becomes really dependent on the antenna. I mean, if you have a metasurface antenna or a parasitic antenna or a liquid antenna, it changes how the MIMO communication system works. And there's opportunities for doing new kinds of analysis, developing new theory, new mathematical models, new fast simulations. So there's a lot of interesting work to be done there. Many people have developed reconfigurable antennas, but I think there's still opportunity to develop more. There's also huge opportunity for machine learning, because what I've done is I've added a ton of complexity here by introducing reconfigurable antennas. So there's a lot that could potentially be learned to configure those smart antennas surfaces even better. And there's new techniques that can be done to estimate the channel, to compress it. So I think there's a huge amount of opportunity here for the tri-hybrid architecture here. And I think it's going to be very important. And 6G development has started. Maybe the tri-hybrid will be the key for making 6G work in the upper mid bands. Or maybe it's too early and we still need to do a lot more work, and maybe it'll be an essential technology in 7G. But I see that this inclusion of reconfigurable antennas, it adds this new intellectual dimension that creates a lot of research opportunities here. So just to wrap up here, so I have been working in MIMO for more than 20 years now. I keep thinking of doing something else, but I'm really just stuck in MIMO, and I guess I'm going to ride it out until I can retire in 20 or 30 years. And I think there's a lot of opportunity. I mean, I think with the tri-hybrid MIMO architecture and exploring new frequencies in the upper mid bands, even going to terahertz, there's going to continue to be a push to make arrays larger, and I think we're just going to see the arrays get bigger in 6G, bigger in 7G, and there's many opportunities for innovating to make those arrays larger. And with that, I will stop here, and I guess we can take questions.